Hello, Algebra 2 students. This is the last lesson for Chapter 1. So we're going to go into a little bit about probabilities. And we're going to be dealing with experimental versus theoretical probabilities. And just a simple explanation. So experimental probabilities, I'm going to abbreviate that there. That's when you actually count. And so you get actual numbers. So for example, if I counted flipping heads and I got 3 heads out of 5 flips, then I would get either 3/5 as my experimental probability, but typically we put that in either decimal or even better, percent. So typically when you'll see me talking about experimental probability, I don't use the fraction. I keep that for theoretical. All of these are correct answers, but experimental probability, you actually do an experiment and record the results. Versus theoretical probability, guess I should have abbreviated that one too. That's what we would expect. So if we did 6 flips on a coin, tails, heads kind of thing, and 2 of them ended up being heads, that would be experimental probability. But I would guess that it would be 3 out of 6 or 1/2 for theoretical probability, assuming the coin is fair. So typically we'll see theoretical probabilities written as a fraction. And that's what you think should happen. It's not what actually happens. So if I flipped it and I only got 2 heads, that would be experimental probability. That would give me 1/3 or 0.3 repeating, or 33 1/3%. Versus I expect it to be 1 out of 2. Every other time I would expect to get heads. So that's just a little definition of the two things. We do run into one other thing in the homework. They ask, what is the sample space? So if I took that very simple example of flipping a coin, the sample space would just be heads or tails. So there's only 2 opportunities, or 2 outcomes. A successful outcome would be getting heads in my previous example. So that's how I got 1 out of 2. So just a couple of terms there just to let you know. And then just in general, probability. It's the number of the events that occur that you're checking out compared to the total possible. And so just making that a little bit more succinct, it's the successes out of the total. So if I would go back to this heads, tails example on a fair coin, the success would be getting a heads. The total would be the sample space of either heads or tails. And so that's how I would get 1 out of 2. And I've got 4 examples to go through. I would say on a scale of 1 to 10, this is not a 10 degree of difficulty lesson here. So here we go. First one. I've got the page numbers. I have to shrink this a little bit. Sorry. Stand by. There. So you can see everything. So this is going with example 1. We're skipping the simulation one, so don't do number 4. We're skipping that. And that's on the WAG again, so you can find that there. So I'll read this for those of you that like to hear it. A player hit the bullseye on a circular dartboard 8 times out of 50. Find the experimental probability that the player hits the bullseye. So they've already done the experiment for us. They're saying they got 8 bullseyes out of 50 tries. So there is the fraction for that. And then we would simplify this. This would be 4 over 25. That would kind of mislead me. I'd be thinking this is a theoretical probability if you left it as a fraction. So I would prefer either 0.16 at the decimal or the 16%. So that's typically how we distinguish between experimental and theoretical in this course anyways. So that's it. Just do the success, which was 8 successes out of 50 tries. And so we get that 0.16 or 16%. So again, we're skipping number 4. That's a simulation. We're not going to go and do those problems. So I'm skipping over to example 3 type of problems. So now this is finding the theoretical probability of rolling a multiple of 3 with a number cube. Now with number cubes, we are assuming that they're just normal, fair dice. So number cube dice, or die for singular, is going to have 6 faces. It's a cube, and so there's 6 numbers, and they're saying, what's the theoretical? What do you think would happen if I'm trying to roll a multiple of 3? So the sample space would be this entire list, 1, 2, 3, 4, 5, 6, and then multiples of 3, that would be 3 and 6. So I would get a 2 out of 6 for my theoretical probability. However, anytime you can reduce a fraction, for me, I expect it to be reduced. So we would say final answer would be 1 out of 3. And that makes sense because there's only 2 choices out of the 6. So that's an example of theoretical probability. Example 4, if you remember back in your 7th grade science class, Punnett squares, P-U-N-N-E-T, Punnett squares, whoops. So this is a problem related to that. Example 4 in the book is very good. It explains it well. I'm just doing another one similar to it here. So brown is a dominant eye color for human beings. If a father and mother each carry a gene for brown eyes and a gene for blue eyes, what's the probability of having a child with blue eyes? So they're wondering the recessive. So the Punnett square, we do make a square. And then if I put, excuse me, the male on this vertical side, and I'll put the female here, so brown and recessive brown. So capital B normally means the dominant, and then B, lowercase b, is the recessive, and then same for the female. So you'll have both those genes, and then each square, it's kind of like you're finding the area. So this is a B by B square, so that's the square that's got both dominant brown eye genes. And then over here would be 1 dominant and 1 recessive, and 1 dominant and 1 recessive there, and then 2 recessives in this square. The dominant wins, so these 3 results would result in brown eyes. This is the only one that would result in blue eyes, the recessive gene. So my sample space for this would be the 4 squares, capital B's, 1 of each. You don't need to list it twice, but I'm just going to put it in there just so you realize, yep, there's 4 of them in there. These 2 are the same. You don't really have to list them, but there are 4 choices. So my theoretical probability for a child having blue eyes would be 1 out of 4. Final answer. All right, just one last example. Definitely the most challenging of the bunch. And this has to do with geometrical theoretical probability. So this is a geometry problem. So you do have to remember your basic circle formula. Pi r squared gives the area of a circle. And the idea is that we're not going to enter skill into it. So we're just going to say it's going to be a random dart thrown at this dartboard. We are going to hit the dartboard, but we're trying to find out what's the probability of just landing in this outer ring. So I'm going to kind of color it here. So this outside kind of reddish colored ring. We're wondering what's the probability if we just randomly throw our dart at this and we're going to hit the dartboard that it would actually land in this outer ring. And so the idea for geometrical probabilities is that we're going to do the area of the success over the area of the total. And some students get hung up on, they want to get answers for the formulas when they put the numbers in. That is really the hardest way to do this problem. It's much easier to do it in terms of pi, and then eventually what will happen is the pi's will cross out on the top and bottom. So I'm going to do the bottom first, and that would be the radius. So I got to figure that out. It says, and this is from the information in the picture here, that each ring equals 2 inches for its radius. So it's 2 inches, then 2 more inches, then 2 more inches, and then a fourth 2 inches. So that makes this, and I'll draw it down here, this radius here for the whole target is actually 8 inches. So that goes all the way to the edge here. So 1, 2, 3, 4 rings, they're all 2 inches apart, so that gives 8 inches for the denominator's area, which is the total area of the dartboard. So that's going to be pi, and then it's going to be 8 squared. I'm not going to get a decimal for this. I don't want to do that yet. Now, the problem with this ring is that it's not just pi r squared. It's actually, if you think of it, it's like a big donut, and I've got to subtract out the whole. So this ends up being a subtraction in the top. It's going to be the big area, but we're going to have to subtract this donut that's got the 3 rings inside it. So again, I'm going to have a pi 8 squared first. That's the whole thing. And then I'm going to subtract out the whole. The whole, I'll draw it in a different color here. The whole is just 3 rings wide, or 6 inches. So that is going to give me pi 6 squared. And so now that I've got it figured out, all right, here's the success, the area of the success. That's this outer ring, and then out of the total area. Now I'm not going to get decimals for this. Instead, I'm just going to simplify these to 64 pi, subtract 36 pi, all over 64 pi. I can subtract like terms here, so that gives me 28 pi's divided by 64 pi's. The pi's cross out now, and I get 28 64ths. Now each of these have 4s in them. They're both even numbers, so you need to reduce this down. If you divide both sides by 2, you'd get it down to 14/32. That's still both even, so I know I can chop them in half again. So my final answer would be 7/16. So a little better than half that I'm going to land in that outer ring, because there's a lot of area in it. And that's how you do a problem like that. You will see one of these on the test, just a heads up. All right, best of luck, and we'll talk to you soon. Bye.